Cool. So do I have to, yeah, it's just share screen. Okay. Share. Cool. And so good morning. So I hope you can see everything that I see, and also the videos will work. Thanks a lot for the nice introduction, and thanks a lot for having me in the summer school. So I think that'll be a very exciting and informative summer school that looks at robot planning from many different perspectives. And I think we all have the feeling that we are currently in a time where we make substantial advance, and I think it might be one of the most exciting times we have seen in the area of robot planning for many years. So I want to talk about knowledge representation and reasoning for robotic agents that have some form of intelligence. That means that they reason about the actions they are doing. So, and I want to invite you to first of all look at reasoning about action from a robot programmer's point of view. So I want to give you some intuition of what it really means for a robot to accomplish a task like pick up an object and place it somewhere else. I want to convince you that if we are talking about programming robots accomplishing these tasks, that it requires the robotic agents to reason about motion. So that means not to stop at the level of atomic actions that have pre and post conditions, but having the methods of AI deeply interwoven with the robot control system. And then I want to talk about hybrid reasoning systems, and in particular ones that tightly couple simulation-based reasoning with symbolic reasoning in order to control the actions of a robot. And then I will show at what are the gains that we can expect from having such a combination of symbolic, sub-symbolic, and simulation-based reasoning. Okay, so let's start by having a look at what are the kind of problems we are looking at. So the kinds of problems that our team is interested in is that we want to accomplish everyday manipulation tasks. So things like making pancakes or similar tasks.
After many years of research, we're now at a stage where our robots can perform complex manipulation tasks, but only in specific contexts, for specific objects, and under specific conditions. The transition should be to mastering human-scale manipulation tasks in realistic and open situations. If we want to go from current robots to mastering activity robotics, the key point is knowledge. The robot will only get key point task descriptions, such as drop something from the pot, and it will need to know that it means tilting the pot, that if it tilts it too much, it will spill, not too high, not too low, and that the weight in the pot will change. The question is, how to get the common sense and naive physics into robot control systems and make it effective so that it basically does its job without delaying the performance. The robot should not have to wait a long time until the reasoning problems are solved. The reasoning should be ubiquitous, so fast that you don't notice that it's there.
Yeah, so this is a kind of thing we would want our robots to do, right? So we would like to install the robots or deploy them in any kitchen environment, give them tasks that we are able to do, and the robots should just do it. So, so the kind of thing that I think we as a community in cognitive robotics should study is, can we have a general model for human scale manipulation tasks, right? By that, I mean, um, a robot control system, we can give a task like set the table, clean the table, load the dishwasher, unload the dishwasher, the kind of tasks that are highly underdetermined and don't even specify a goal state. And we would want the robot control systems to perform these tasks in an end-to-end fashion. So meaning that this underdetermined task is sufficient, that a robot control system is executing a perception action loop and implementing the underdetermined task in a specific environment using its own body. In addition to being able to accomplish the task, we would also like the robots to get better and over time, right? And the means that it has to get better over time is that it should learn from experience. So if it accomplishes manipulation tasks many times, it should have a good idea of how it has to parameterize its motions to make them successful. It should use knowledge and reasoning. So when it sets the table, it should put only clean cups on the table that are not used by others. Um, it should kind of decide on how to accomplish actions with foresight. So when it picks up an object, it should pick it up in a way that it doesn't have to regrasp in order to put it down. It should learn from observing others, in particular, uh, learning from humans, because humans have a lot of common sense and intuitive physics understanding, and it should be able to learn from being told, right? So that is important. Because being told means that we are giving very abstract pieces of information, and then the robot has to find out how to take these abstract uh, pieces of information and make them actionable in its own control program. Another very important capability for me is that our robot control systems should know what they are doing. So by that, I mean um, that the robot control systems also have an open question answering system where you could ask at any time, what are you doing? Why are you doing it? How are you doing it? What do you expect is happening when you do it? Are there alternative ways of doing it? So it's pretty much like a Siri agent, right? Where you can ask any questions about the ongoing activities. And this is important because robots need the introspective capabilities to be robust and to be efficient and to be able to recover from failures when they are happening. So in the last part of the video, we have seen kind of the robot doing popcorn, and that looked very nice. But that was kind of the decision making was very limited to that particular task and and that particular setting and that and the particular object that were used in that scenario. So what I want to now show is how we are doing when a robot is reasoning about everything, and so we are basically now looking at fetch and place tasks, and a robot doing the fetch and place tasks in very different contexts, namely in the context of setting the table and cleaning the table. So this was a milestone experiment we did last week. And just to give you an impression of how the behavior that can be generated.
And I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called Giscard. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach, such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick and place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collected experience. For more information, please follow the links in the description below.
Cool. Yes. So basically, I think the messages that should be taken from that video is that every action that the robot was executing was planned using some form of robot planning, and it kind of none of the parameterizations of the motions were really hard-coded in that system. So the system was, of course, speeded up heavily, but I think it gives you some impression of what can be done using today's technology in terms of generating varieties of behaviors and generating them in the appropriate context-sensitive manner. And so what I want to talk about is the knowledge representation and reasoning capabilities that make that kind of behavior possible. So before I can do that, I just want to go briefly through the architecture that we are using just to understand the context in which the knowledge processing is taking place. So our system consists of a plan executive, which uses generalized plans for action categories. So for fetch and place, the system is equipped with one plan that is general enough to kind of accomplish all fetch and place tasks. And that action plan is combined with the motion plan. I will talk about a little bit later. And so this plan is formulated in a very generalized way. So the plan executive has to ask, if it has a certain action, how should I move my body in order to accomplish that task? And this is a task of the knowledge representation and reasoning system, right? So you can imagine the knowledge representation and reasoning system to be something like a Siri agent that is waiting for questions and giving all the answers. But in this case of a robot agent, the Siri agent is fully embodied. It's linked to the perception system, and it has to give its answers in ways that can be executed by the motion control system, right? And the other components are the perception system and the motion control system. So how do our plans look? So for fetch and place, we have one generalized plan schema. And that plan schema basically says, I have a plan fetch and place for transporting any object from the place where it's currently at to any destination. And in order to do that, I have to be at the location where that object currently is and perform the action fetching with that object. And at the destination of the object, I have to put it down. So this is formulated in a very abstract and general way. So what is meant by that plan is, so at a place from where you can see and reach the object, you have to select the appropriate grasp type, grasp points, reaching motion, grasp force, and so on. And with the appropriate parameters of the motions, you have to reach for the object, simultaneously form a pre-grasp, and then close the gripper. You have to wait for the object being grasped and lifted, right? And the hard part about that thing is that we are specifying appropriate way, because appropriate way means that we want to have a parameterization that achieves the desired effects and avoids the unwanted side effect. And this is the heart of robot planning, right? When we are reasoning about the future execution of actions in order to avoid failures and to make our actions successful. So at the motion level, we are also having for each action category like fetch and place, cut, pour, a generalized motion plan. That motion plan is structured according models that come from cognitive psychology of human manipulation actions. So in the case of fetching and placing an object, the motion phases are the reaching phase, the lifting phase, the transportation phase, and the releasing phase. So for each of these phases, we need a specific sub-action controller. And each of the major sub-actions has a sub-goal that has to be reached in that respective motion phase. So for the reaching phase, when we reach for an object, the goal is that the hand has contact with the object. For the lifting phase, that the object is lifted off the supporting surface and that the weight of the object is felt in the hand, right? And so each phase has a goal, And if that goal is reached, the overall controller switches to the next phase. And what is also important is if we are executing motions, we have to parameterize the motions. And that parameterization has to be done at the beginning of each motion phase, right? So the parameterization, so the execution is fluent, and it's only possible if we basically set the parameters in the beginning. So for the reaching phase, right, so you are in the situation where the robot has seen the object to be picked up. So the robot decides for the pre-grasp pose of the hand, the grasp pose, the points where the fingers have to be in contact with the object to be grasped, and the force. And we might have additional constraints such as staying away from fragile objects or keeping the hand upright, or these additional. So each of these motion phases has its parameters, and if these parameters are not set, then the motion phase cannot be executed. So the purpose of the high-level plan is then to determine these actions. So as we have seen in the beginning, the action descriptions are abstract. We say pick up any object, right? And the question is, how can we resolve such abstract descriptions of objects? So in this video, we see how an object is picked up and how the robot infers the specific parameterizations of the actions in order to execute it successfully. So it starts, it knows that the object is to be found on the countertop, and countertop are all the red areas in the video. So the only thing that it can do is it samples positions on the countertop, and in order to find the object, right, it has to then commit to a location from which it can see the sampled point, right? And you see that here. Then it positions itself there, performs perception, gets a camera image, exercises its object detection routines on that, and cannot find the object. So then it has to basically sample again. Now it has found the object, right? Now it basically goes to a location from which it can reach and see the object, more exact enough to pick it up. That's what's done here. And it's executing the grasp action, right? So, but that is essentially what's going on when we are executing the plans that we have seen in the table setting experiment before. And you see that when the robot is acting, it's doing its backtracking in the physical backtracking, right? So this is what we are doing, and I call that essentially knowledge-based robot programming. So we have that generalized plan that specifies the activities in a very general way, and we combine it with a knowledge base with generalized knowledge pieces, right? So, and the knowledge pieces, they are of very different categories, right? So some are about where can I find cups, or specifications such that cups that are used for table setting have to be clean and not used by somebody else. Cups have to be grasped from the outside. So these are things that are mostly common sense knowledge, or specific domain knowledge about the environment model and where I can find these things. But there are also very general and very powerful knowledge pieces. So something like you want to parameterize the motions to avoid unwanted side effects, right? And spilling is an unwanted side effect. So this is a very powerful, these two knowledge pieces are very powerful, right? Because they entail that the robot has to mentally predict the future, right, and decide whether there are unwanted side effects, and depending on whether or not there are such unwanted side effect, adjust its parameterization. Or another very powerful knowledge piece is the pose from which I can pick up a heavy pot. So this is very powerful, because I think the most promising way to obtain such a knowledge base is the experience of robots, right? So many tries where the robot tried to pick up and carry different objects, and from these experience, it can learn the pose to pick up a heavy pot. So, and then the game is, right, so we have these generalized plans for fetch and place, but now we want to make our knowledge base powerful, so powerful that we can execute that generalized plan with very high expected performance. Okay, so if you're not convinced yet, let me just give a couple of other arguments why you don't want to stop with knowledge representation and reasoning at the action level, but that you want to go all the way down to the motion level. So the first one is we have to close the knowledge gaps, right? If a robot gets an instruction such as perform a pouring action with some water, and this is the scene, the pot with the vegetables that the robot is seeing, it has to infer the motion parameters and the constraints such as grasp the pot by the handles, hold the pot horizontally, tilt the pot around the axis between the handles, remove the lid before, and if a robot control system would not infer these motion constraints, there would be no way that a general task like that could be successfully accomplished through a robotic agent. The second reason that we have to look at the motion level is that if we are looking something like actions like adding milk to the dough, the same description of an action has to be or can be realized in many different ways, right? And the robot has to reason about which of these implementations to choose, also because the tools that it might have available might differ from what is originally predicted by the programmer. The third challenge is that if you're looking at manipulation actions, it's often the case that manipulation actions rely on manipulation twists. So certain behavior modifications you have to do in order to make the action successful. So in the case of flipping a pancake, if you don't push the spatula onto the oven when you try to push it under the pancake, so you will have all kinds of failures and a mess that the robot produces when executing the action. And so this manipulation twist is for many manipulation actions the aspect of the action that decides over success and failure, right? Or in the case of pouring, if you're pouring too close to the border of an object, the probability of spillage will be higher. So how is the control system then working when we are executing the plans? So in the table setting experiment that we have seen, typically we have an action like fetch the next object that is missing on the table and place it on the table at the appropriate form. So we get instructions like perform an action, fetch and place with a cup, and where the destination of the cup is a kitchen table, right? So if we are getting a call to our plan like that, we are taking the specific informations like an object type cup and substitute them in our general plan, right? Then we know that what the robot has to do is it has to determine a body motion that accomplishes that action, right? So, which means we have to take all the parameters that are knowledge preconditions of the motion phases of the motion plan and add them to our partial action description, right? And then the plan executive is asking the question of what are the values of the parameters that I have as the knowledge preconditions of my motion plans that make the execution of this plan successful. And that's kind of the heart of the system. So any action that our robot was executing in the table setting scenario was actually executed in this way. So typically that process is more complicated, right? Because the knowledge precondition become available at different points of time. You only see the spoon in a drawer after you have opened it. So you also need to execute actions to acquire the knowledge, right? But we are abstracting a bit from those issues. So really the role of knowledge representation and reasoning in a robot control system is in our model that you have that motion model for fetch and place tasks, the motion plan for fetch and place tasks. You have that underdetermined high-level description of an action you are supposed to execute successfully, and closing the gap between these two is what you need your knowledge representation and reasoning system for. Okay, so now that we have clarified what our knowledge representation and reasoning system has to do, so we will now look at a little bit at what do knowledge representation and reasoning systems have to do in order to provide that service. And I think that requires a new generation of knowledge representation and reasoning system, which are particularly tailored for being embodied in robot control systems, and also that have the power of reasoning about geometry and motions, and not only about actions in the abstract. Okay, and this is now the system that I'm talking about, and that's a system, it's called NOROP2, and we have published on that. So the idea is that NeurOp2 is a hybrid knowledge representation and reasoning system that combines symbolic knowledge representation with sub-symbolic ones. And it's composed of different layers. In the center, it's ontology. And then we have a hybrid reasoning kernel with different forms of reasoning. The hybrid reasoning is encapsulated with a common interface language, which is essentially a first-order predicate logic language based on time interval logic. And then we have the applications sitting on top of this interface language, which are question answering, perception, recording of experience or episodic memories, and learning. So I will just briefly go through the system. So important is if you are looking at a robot control system, to put an ontology or an encyclopedia, a knowledge base that defines all concepts at the center of your knowledge representation, right? And the reason you want such symbolic representations is that this enables robots to make syntactic inferences that are semantically meaningful. So the ontology is the thing, the Wikipedia, the machine understandable Wikipedia that makes all the computation processes capable of doing their computations at a semantic level. So around that, we have three different forms of knowledge representation. One is symbolic knowledge bases. So these are exactly the way knowledge base, knowledge representation and reasoning is, for instance, taught in the textbooks in AI. So another component is the robot control system, right? So if you think about a knowledge piece like the current position of the robot in a robot control system, this assertion is not something that only exists in the abstract, right? But you have actually a localization system running on the robot that computes the position, right? So what you want to do is you basically want to use the computation mechanisms that the robot is using and cast them as a virtual knowledge base. So that basically the symbolic knowledge base and the data structures that drive your robot around and control your reaching and manipulation actions are consistent with what you believe about the world, right? And the third component is essentially an inner world model. It's basically a representation of the world that you can imagine, just like representation in a game engine, but it's machine understandable. So we have that logic, interface language, and the applications. So let's look at the ontology that is at the heart of the system. So kind of here, it basically is important that all important parts of the control program and the environment and the robot's capabilities are defined explicitly in your knowledge base, and that if you have different system components like the perception system or the motion control system or the reasoning system or the planning system, if they exchange data structures, right, the data structures have to have a common meaning for the whole system. And the ontology is a part of the system that ensures that. So the ontology you can imagine as a machine understandable robot encyclopedia. So you have many different concepts like containers, bowls are containers, a milk box is a container that is filled with some substance. And all these different components, like they are concepts in the ontology. And the ontology also um, uh, defines the relations between these different concepts. So if we are looking at the instances here in that image, we can say that the bowl is supported by the tray, that the bowl has a quality that it's not quite stable, so it's wobbly, and we also have other parts of knowledge that uh, that are specified in that encyclopedia, something like the physics of solids, where we have friction, weight, and roughness, and these kinds of things, and the physics of fluids. And so by combining the data structures that your robot control system is using to these concepts, uh, the robot can automatically uh, assess all the knowledge about these respective concepts that the data structures mean. Right? So that's kind of the idea. And if you think about robots, you need knowledge about many different aspects, right? About sensor data, the body of the robot, the perceived object, the controller state, and software descriptions, action descriptions, environment maps, and all of these pieces should be machine understandable because they are all heavily related to each other, and different subsystems like the perception system, the control system, need different information aspects of these concepts in order to work properly. Okay, the second part of the knowledge base is that idea of virtual knowledge base. So the model you want to build about what the robot is doing and about the environment is basically contained already in the data structures of the robot. So the problem is that the encoding in the data structures is implicit. So for instance, if we are looking at information about the robot's position, that's typically contained in a probability distribution over the robot's pose in the environment, which is, for instance, computed through Bayes filters. So what we want to do is we basically want to provide a symbolic abstraction of these data structures that are semantically meaningful. So if this is the current probability distribution over the position of the robot in the environment, we might want to define predicates such as the robot is well localized. If we look at the distribution of the robot position and we only have one big global maximum, then we would say the robot is well localized. If not, it's not well localized. We can also extract the belief about the current pose of the robot by taking the probability distribution and returning the maximum of the peaks of the distribution, right? So that's kind of fairly straightforward. And you would do that with all kinds of data structures and computation of your robot control system, right? So for instance, if you're thinking of a predicate whether an object is reachable, one way of grounding it in the robot control system is that there is an inverse kinematic solution of reaching the pose of the object, right? Yes, so symbolic knowledge bases are extremely important in robot control systems, because if you look at robots, we want to have robots that act in different environments. They might be outdoor, they might execute their actions in laboratory environment, and they perform different tasks such as experiments, search and rescue, and they even might be a kind of different kinds of robots, like flying robots, PR2-like robot, surgical robots, and so on. And what you want to avoid is that you have to write your robot control program for each combination of task, environment, and robot, right? And the way to do that is by equipping the robot with knowledge bases about environments, robots, and tasks. And then the robot should figure out how to do things concretely with its own reasoning system. So for example, if you have a drone that is supposed to fly outside, you want to use OpenStreetMap or a similar knowledge base that already exists in the World Wide Web as a knowledge resource for controlling the robot. Okay, now let's go to the interesting part, and which is the way of how to represent the belief state of a robot while executing the actions. And so I guess many of you know that some of the models in cognitive psychology, they are linked to an idea that you might have an inner representation of the world where you can simulate what's going on when you physically execute an action, but you're using that inner world actually as a knowledge resource to perform your actions in more informed way. So a prominent researcher arguing heavily in this direction is Heslund, who says thinking is the simulated interaction with the environment, right? So the idea is you get sensory input, you have internally a representation of that sensory input, you map this representation of the sensory input to the response to the sensory input that's converted in the real response and executed physically, right? And the idea is that you can shortcut that and you can have an internal simulation where you simply connect the representations of the responses and representations of the symbol inside without having to move your body. And that's, as we will see, an extremely powerful way of thinking about knowledge and representation systems about the beliefs of robots that can represent the beliefs of robots. So the idea is that if you look at the knowledge base and the representation mechanisms of robotic agents, that we do not only have a symbolic knowledge base, but we have a pair of knowledge bases, which is, for one thing, the symbolic knowledge base here, and the second part is an artificial world that you can imagine just like a game engine representation of the world the robot is acting in. And in that game, in that artificial world, the robot also has ways of rendering the artificial world and physically simulating that. So these two knowledge bases are tightly connected to each other. And in the way that the data structures we use in the artificial world, they are given symbolic names, and the symbolic names are then used in the symbolic knowledge base, and the symbolic knowledge base also connects the symbolic names to the ontology that defines the background knowledge about these objects, right? And the idea is that you want to basically have your artificial world such that it's kind of resembling the real world as closely as possible. So, so how are we going to implement it, right? So if we are thinking about symbolic knowledge representation, the language is defined recursively. So you basically have a set of simple names that are all the entities in the world that you can talk about, right? And you are to basically define them typically manually, right? So here we are going differently. So we just take the scene graph representation of the world and say everything that is in the scene graph is actually a symbolic entity. So yeah, so that means if you're looking, for instance, at the fridge, so because the scene graph of the fridge is extremely detailed, we have entities like the door of the fridge, the hinge of the fridge, that the fridge has glasses, and the construction of that symbolic knowledge base is easy and straightforward, right? So we take the scene graph representation of the world as it's represented in the game engine. We walk through that scene graph, and all the entities that are relevant for the robot control system, we give a symbolic name and we connect the corresponding entity to the ontology of the symbolic knowledge base. So that's kind of fairly straightforward. So what you want to do is now, so you have basically that artificial world, and which is a scene graph representation where everything is made machine understandable by kind of turning the data structures explicit by giving them symbolic names and linking them to the symbolic knowledge base. So this artificial world should match exactly the real world that the robot is acting in. And so the robot control program should be able at the same time to act in the artificial world and to act in the real world. And what we want to have is that that both of them are so close to each other that the robot control program could not determine whether it's actually executing the program in the artificial world or in the real world. So of course, kind of we never get that close correspondence, so we have to pay for that by equipping the robot control program with a heavy load of event and failure detection and continuation. But the hypothesis that we have is that this is worth the price. And so what we are doing is we basically are in a mode of execution where the robot control program is believes that it's executing its program in the artificial world, but indeed it's executing it in the real world. And the reason that this is a good idea is, of course, that the artificial world is fully observable and we have exact knowledge about that. So, so that's kind of in theory quite interesting, but the question is, could that actually work and fly, right? So, and the key question is it possible that we can construct these artificial worlds with robots automatically so that they can serve as belief states? And for kitchen environments, it's not, but there are real world environments where we are getting capable of doing that. And these are mainly retail stores environments, right? So we are installing a robot in a retail store. The robot is scanning the environment. So here on the right-hand side, you see the belief state of the robot. At that point, it has detected the basic shelf system. It has detected the individual shelves, and it has reconstructed the model that the shelves are connected to the shelf system. So it reconstructs the environment in a compositional way. So now it's basically looking at the individual shelves, looking for the separators, looking for the barcodes. It's cutting that and adding that, and now it's looking whether it can find the products in the respective facings of the shelf, and then it can populate uh, its environment model. And this environment model is a knowledge base, right? So we can ask questions like, where is a particular product? And it's this query in a little bit modified Prolog syntax, and it would highlight the object here. We can ask questions like, where are empty facings in the shelf system, so that it knows where it has to refill the shelf. We can ask, by combining it with the background knowledge in the ontology, we can ask questions like, where are the products that are health-threatening to kids, but in the reach of kids, and you would find the cleaning materials. So the story is that the robot can basically go in your environment, build a knowledge base, an environment model of that, and answer these questions without manual interactions through programmers. We can also recreate the whole system as a virtual environment, and you can go shopping in the model that the robot has constructed. And because the whole thing, again, is a knowledge base, we can also automatically interpret the actions that are executed. So here you see, for instance, the actions, how the person has picked up the objects and put them into the shopping basket, and so on. Yeah. So for roboticists, I think the hallmark of doing that environment mapping is, can we have an environment model that enables the robot to do meaningful manipulation actions in the environment? So something like fill the empty shelves, and for particular objects, we could show that we can do that. And here you can see that the whole technology also scales towards real environments where we build these models, these artificial worlds for drugstores that, yeah. Okay, so so in general, kind of, I mean, there is a lot of work to be done and a lot of research to be done to scaling that kind of capability to environments like kitchens or apartments. But I think in principle, one could actually see that these kinds of knowledge bases for robots could be constructed automatically by robots. In particular, if we see the very fast and disruptive progress of deep learning systems in pattern matching tasks, right, which would be the workhorse for such applications. Okay, so so this is one thing, right? But in that experiment we have shown, you have already seen that the system was using such a belief state representation and executing that. So this is actually the question of, say, we have an environment map of our kitchen environment that was built the way as the robot in the retail store did it. So now, if we have that as a starting point, could the perception system of the robot control system actually maintain the belief state during the execution and keep the environment model up to date so that the robot can accomplish that manipulation task, right? And this is possible, right? And the reason that is possible is because we have the artificial world, we can render the current belief state as an image. The image is the image that the robot expects, and the robot can compare the image of what it expects with what it's seeing. And everything that is correctly predicted, it doesn't have to process again. It's only the discrepancies between both that happen. So here you see, oh, sorry, the video is not, but essentially you can see that we have an object detection system that exploits that we know all the objects in the environment, that we have cut models of them, and we have a deep learning system that was trained by placing objects at all places that are meaningful in the artificial world, with physics engine turned on. So we only look at places at configurations that are physically stable, and we learn essentially to detect the objects in the respective poses in those settings. And this is possible, and at least for the kind of variations that we needed for our experiments, so we could learn the object detection capability and the updates of the belief state using these experiments. Okay, so then the other question is, okay. So here, so you see on the right-hand side, the robot executing the actions in the real world. So the left-hand side is a rendering of its belief state of the artificial world. So the left-hand side is actually a symbolic first-order logic knowledge base, and everything that you can see on the left-hand side, you can access through a prologue predicate. And now we can see what is actually the belief of the robot of what is happening in the real world by just looking at the video that is generated out of the symbolic belief state of the robot. So what is happening is that in the belief state, the system is telling that the robot has grasped the object, right? And this is implemented in the belief state of the robot by attaching the object to the gripper of the robot. And now, because the robot is getting the data of how its hand moves, it also knows that where the object is in the mid of grasping. So, so what we are doing is we have actually three processes running, right? The executive that is executing the action in the robot control system. We have the perception system that is trying to recognize everything that is happening. And we have the mental simulation in the belief state of the robot. The mental belief state tells the perception system about what it expects to see. So for instance, the object being in the hand. The perception system tells the mental simulation about newly detected objects and things like that. The mental simulation tells the executive about the predicted world state. So for instance, if the robot reaches for a handle, that it predicts that a handle to be grasped. And the executive tells the mental simulation about which commands it has executed. So for instance, it has closed the gripper. And the executive and the perception system are also coupled this way. So let us look at what kinds of beliefs that make the situation where the robot is opening the container with a waste basket and picking up the milk box. So now, kind of the thing that we have in the belief state, that when the hand moves, the drawer is actually opening. And we have that in a continuous state during execution. We also have the thing that so that if the hand is opened, the object falls into the waste basket, and this is because of the physics simulation in the belief state, right? And which would basically give the robot the information of looking for the object after it has lost it, and if we are basically sampling different parameterizations, we would also know that this is not the exact location that it can use, but it has to look somewhere there. So this is the idea of how we want to bootstrap the knowledge that a robot has about execution and monitoring manipulation actions that go beyond what current perception systems can do. And we can do that because we have running a physics simulation on the belief state. And yes. So here you also see that we want to basically simulate some physical motion, so that we want to form expectations that we expect kind of the milk to be in the glass after pouring it, or we want to basically predict the effects of grasping. And by having that running in the belief state, we hope that we can basically inform the robot with the respective information. Okay, so let's then come and so we have seen that we have now at least promising ways that we can implement belief states of robots that are detailed enough, maybe realistic enough to give better information to our execution system. And I just want to give an example of if we are recording all these episodic memories of manipulation actions, how we can build up the knowledge bases of future robots, right? So when you look at our robot control system, whenever it's executing manipulation actions, it's essentially doing a brain dump. It's recording, similar to the autonomous cars at the moment, everything that is in form of data going through the system while executing that. So this is a video that is generated from the log data in the belief state, right? So, and you see that we can, from the symbolic representation, reconstruct the motions with some continuity. We are getting the images that are used for detecting objects, but we also get records of the execution of the plans, the activation of the motion plans, the parameterizations of the motion plans, and for everything, we also get the semantic descriptions of what is happening in terms of symbolic descriptions that are basically a side effect of the plan executive executing the plans. Okay, so this is a kind of data structure we are creating whenever we execute plans. And these data structures essentially include at the subsymbolic level all the images that the robot control system used in order to accomplish perception tasks. The poses of the robot, so the TF tree in your ROS system is automatically recorded. Then the plan interpretation system records the way the different code pieces are called and what the computation state of each code piece during execution was. So what is very important is the events that connect the subsymbolic representations with the symbolic ones. So these are typically the force dynamic events, something like the hand touching the object to be picked up, the object leaving the supporting surface. And these are the points that we need in order to synchronize the subsymbolic data with the symbolic data that come from the plan interpretation system, right? And for each of these events, we basically assert a small knowledge base that describes the event. So here we have a perception event. So we basically specify that a certain event occurs at a certain time instant. The event type is a detection event. The perception task is described in this data structure. The data structure is looking for a certain object. The result is this data structure, and it's basically described here. The image that was captured and that was used to extract that information is this one, and this object description refers to that region in the image. So it's a perfect symbolic knowledge base that is recorded for that perception event. So now, if we are having these episodic memories that are automatically recorded, we can see what can we do with that. And so we can simply ask symbolic questions. So we can, for instance, ask the prolog query, so give me a task where the action of this task is an action of the type pickup, and the object acted on is an object of a type pod, where the weight is a certain weight, but that weight has to be more than 2 kilograms, right? And we are interested at the time instant where this action has started in our log file. And now we want to know at that particular point, we want to know what the pose of the PR2 at that particular point was. And we get from the TF tree at that instant that pose, right? So now we can use that for automatically making up learning tasks. So for instance, so we can basically ask, so this is the query we just had. And now we are looking for the set of poses in which the robot performed an action in which it tried to pick up a heavy pot, and the task outcome of that task was success. And we are collecting this pose in poses, right? In the variant. So we collect all poses from which the robot started to pick up a heavy pot successfully. And we can do the same thing for the instances where the robot failed. And now we have our training examples for learning where should the robot actually stand in order to pick up objects successfully, right? So we are executing in simulations many different table setting episodes, and for each of them we record whether the respective pickup actions were successful. So here you see the objects being at different places on the table. The green ones are the successful attempts, the red ones are the failed ones, right? So now we basically get the samples for each possible position of the object on the table. And you see here the different examples of getting these data. And now we learn a classifier, which is the location from which the object can be picked up successfully, right? So you can see that's matching our intuitions. If the object is going more to the front, the place from which it can pick up successfully becomes bigger, right? So now it basically can learn the places from which to pick up the object successfully. So if at execution time, the robot detects an object and estimates the pose is has some uncertainty. So it can sample object positions from the expected uncertainty, back project the place from which it can pick up successfully, and it gets something like a distribution that estimates the likelihood that the particular action is successfully will be successful when standing at that particular location. So this is kind of the form of distribution you expect. And here you see how that distribution actually changes when you move the object or you change the inaccuracy of the position estimate of the robot or the pose estimate of the object. Okay, and now we can take that learned concept and inject it in the perception action loop of the robot. So here you see the robot entering a room, and it's supposed to pick up the objects from the table. So it assumes that it has detected an object here, and the place from which it can be picked up would be here and with a lower likelihood here. So when it comes closer, it suddenly notices that's not one object, but actually two. So the place from which it can pick up both of them is smaller, but it's also updated on the fly. Now it detects that here is an obstacle, so it has to grasp this one here and later has to go around to pick it up from here. But the bottom line is, if you have that kind of system, right, so then you have the capabilities in particular with modern machine learning methods, that you can define concepts symbolically in using our symbolic infrastructure. You basically can collect all instances of that concept in the episodic memories that the robot have generated through the activities, and turn each concept that you want to learn into a learning problem that can be learned through supervised learning, right? And in particular, we have published a paper where we can go and take all the decisions that the robot has to make in order to execute a general pick and place task, and learn them, and could show, if we are learning them, then the performance of the robot control program is substantially better. Okay, so besides kind of getting these completely new reasoning capabilities and learning capabilities, and being able to ground symbolic representation much tighter into the execution system, I think there's another aspect that makes these artificial world-based knowledge representations exciting, right? So, and I think that this is, if you're looking at robot control systems right now, so typically you have different subsystems that have completely different data structures that don't have to do anything with each other. So you have the symbolic knowledge base, which represents the world as a state transition system with atomic state transitions, right? So you have the perception system that represents the world in terms of pixels, regions in the image, and maybe some category labels for attaching to regions, right? And you have the motion control system that represents the world in terms of reference frames, which is just 6D poses, and that may be connected to each other through link structures, right? But one of the key problems that we have in robot control systems is that these different representations are completely unrelated to each other, and this is also, they actually refer to the same things, right? So we just want to execute actions in the real world, right? So I think another very promising property of these new forms of knowledge representation is that the representations that are used in control theory, the reference frame representation, the pixel representations, the symbolic representation, but also the simulation and rendering representation, they all can be constructed out of the scene graph representations, right? So it might be the case that these kind of representations of the environment and the beliefs of the robot because they are so detailed and that they are actually, that they could become a common ground for combining the different areas of symbolic reasoning, of perception and motion control. And I think that's kind of something we should look at. Okay, so this is the end of my presentation. As Malik said, we are trying to get all of our results in an open web service then that you can access. So we are currently, I think, after our milestone experiment, we are completely re-implementing the open ETH web service so that you can access all the data from our experiments. And I guess this will be ready hopefully in a month or so. So I would be very happy if you look at our research, and I hope you found the information in that lecture somewhat useful for your own research. Thanks a lot for your attention.
Many thanks, Michael, for this very broad and comprehensive view. I guess that many of the school students have a very focused interest on some of the aspects that you mentioned, but it is very good that they get right from the end such a global picture about how their work will need to fit if they are interested in robotics and interaction with the real world, with or without robotics. So I see that there are some comments. Maybe we can turn off unmute everyone and let some of the students ask questions to Michael.
Yep, you'll be able to unmute yourselves if you want to ask a question with your voice. Otherwise, just write it in the chat. So, Michael, I see there's already one question from Mustafa. He's asking, is the ontology used to act in the real world used as a basis for the game engine to act in the virtual world, or how are they linked?
So, I mean, the perception system is updating the artificial world all the time. So the real world, so the perception system dictates how the artificial world develops. And at the same time, the actions that are executed by the robot control program, they are asserted in the belief state as assertions, right? So the robot has grasped the object, and then the simulation and the rendering of the belief state of the artificial world kicks in order to make predictions of how the real world should look, right? And then the perception system can see whether the internal predictions are matching the reality. And if that is the case, it basically has the complete accessibility of the state in the artificial world available to choose its action parameterization, right? So it has a lot more information available. Is that understandable?
I think so. Ronan Brafman and Oscar Lima ask related questions. Ronan asks, is the code for the simulations of the various manipulation tasks available for use, and are the simulations done in Gazebo? While Oscar asks if you need knowledge of Prolog and ontologies to use NoRob. Sorry.
Yeah, so yeah, if people are interested, they should contact the developers. So we are making all code available, but we make it available after the code is ready, right? So typically after a milestone, we have to go through the code again to make it actually usable by others. So yes, so for all components, there are versions of the system that are already available open source. It might not be the version you have seen in the video, and there might be a kind of a delay until that becomes available, but you have to ask that the particular people. Yeah.
Okay. Siddhant Bambri asked, how do we incorporate the robot? How do we incorporate and the robot differentiate between stochastic and probabilistic knowledge if it is added to the symbolic knowledge base?
Okay, so there's I have talked about only the planning view, right? So basically about the choice of motion parameters that are executed, right? But then the implementation of these motion plans, they are reactive, robust systems that where you go into the haptic feedback loop and you have all this uncertainty going on. And this is a part I have not talked about, right? At our level, you get uncertainty and also probabilistic models by learning over the collection of episodic memories and or by sampling different predicted scenarios and doing that. So, but at that level, it's probabilistic reasoning by sampling, right? And that's because the simulation mechanism is so dominant in the system.
Michael, a question from Sarah Kiran. How does your framework account for user preferences?
Oh, so I've not talked about human-robot interaction, or is that about user preference, or so we can. So it depends on which ones, right? So one way we can learn the knowledge from the environment is by letting people set the table in a virtual environment. And this way we would actually get information about preferences of humans by observing how the humans perform these activities. But we haven't done any research in how to represent preference models or something like that. Yes.
All right, we need to leave some time for the break such that everyone is fresh for the next lecture in about 20 minutes. So thanks again, Michael. I wanted to point out that some of the basic building bricks in terms of technology and algorithmics will be covered by other lecturers during this week. There should be a link to the lecture on Wednesday morning. This is lecture 5 by Fabiana Grifoul on the combination of task and motion planning. I believe there should be also a link with the lecture given by Joachim Erzberg, which is lecture 9, task-based robot control, with what you presented. This is on Thursday at 10. And there will be also a relationship between what you presented and the presentation on the overview lecture that will be given on Friday at noon by Manuela Veloso. And last point, please, if you have on second thought additional questions or some of your questions we had no time to cover, you have the Slack channel for lecture 1. Go there and leave your question. I'm sure Michael will cover that. And Michael, please add some of the references you mentioned to your slides when you will send them because they will be very useful to everyone.
Yes, I will do that. Yes. And
Thank you very much.
thanks a lot for your attention. Thanks a lot for the questions.
Thank you for your very nice and illuminating talk. So see you all in about 20 minutes.